This is a presentation about fire safety in tunnels. The question is, are suppression systems the answer? My name is Dr. Ricky Carvel. I am Assistant Director of the BRE Centre for Fire Safety Engineering at the University of Edinburgh. And I'm going to start my presentation by giving you the answer. The simple answer to that question, are suppression systems the answer to fire safety in tunnels? We don't know. And now let me explain. An overview of the presentation. First, I'd like to talk about fire safety management. What do we actually want to achieve for a safe tunnel? Then we'll look at suppression systems. How do suppression systems help achieve the goals of fire safety management? How do suppression systems hinder the process of fire safety management? I'll give some conclusions, and then right at the end I'll talk about suppression combined with other systems. But that'll just be a quick comment. So, with regard to fire safety management, what do we want to achieve? Well, ideally what we want to achieve is a tunnel with no fires in it. If we can, we want to prevent fire happening in the first place. In reality, of course, that doesn't always happen, so we want to minimise the fuel, which may mean controlling the vehicles going into the tunnel, identify potential risks, potential issues that can be weeded out, so that we can minimise the risk of fire or minimise the risk of a large incident happening in a tunnel. We also want a safe and smoke-free egress path if there is a fire. Ideally we don't even want to have to evacuate, but in the current state of the art, if there's a fire incident in the tunnel, you will still have to evacuate. And when you're doing so, you want a safe and smoke-free egress. We also want efficient firefighting, which would mean a clear route so that the fire brigade can get to the fire location, and also ideally the fire as small as possible when the fire brigade get to it. We want to protect the facilities, and we also want a rapid return to normal operation, because a fire is exceptional circumstances, and in those circumstances the tunnel is not able to be used for its normal job, which is to get people from A to B as quickly and efficiently as possible. So the question is, how does suppression help achieve these goals? The goals of fire prevention, safe and smoke-free egress, efficient firefighting, protection of facilities, and a rapid return. And I'm not going to talk about all of them just now. Specifically, I'm not going to talk about fire prevention or the swift return to normal. But let's talk about suppression versus fire. And the question is, what research has been carried out so far regarding suppression systems and fire? When it comes to the influence of suppression systems on fire size, some limited research in tunnels has been carried out. But limited research only gives you some limited knowledge. When we're asking the question about suppression versus fire spread, we only have a few observations there, and a few observations only really gives us anecdotal knowledge. The same can be said for suppression versus fire growth. A few observations from a few tests does not really give us much in the way of knowledge, certainly no understanding of the real world behaviour of these systems. And when it comes to considering, say, suppression systems with ventilation systems, which are generally installed in tunnels, no research has been carried out at all. No research means no knowledge. There are largely two kinds of suppression systems: sprinkler deluge systems and water mist systems. Sprinkler deluge systems have been performing very well in Australia and Japan for many years. Japan have been using them for 40 years. Australia in the past decade or two have had suppression systems, deluge systems, in all their road tunnels. And these are generally shown to perform very well in tests and indeed very well in practice. In the Burnley Tunnel fire in March 2007, a fire was started as some vehicles collided. 3 people died in the crash. There was a fire, the suppression system was activated quickly, and as the suppression system operated, the fire was maintained, or it was confined to just the locality where it had started. 400 people safely evacuated from the rest of the tunnel with no further injury. But that's only anecdotal knowledge again, very little scientific testing. When it comes to water mist systems, we're seeing them becoming increasingly popular in Europe in particular, and In some tests, they are seem to perform very well, but that does depend on what you consider your success criteria are. Many tests use fuel pools, and does that actually tell you anything about a water mist performance on a real vehicle fire scenario? I'm not sure it does. The main difference between the sprinkler deluge systems and water mist systems when it comes to dealing with fire is the size of the droplets. Here we have some sort of stylized fire. The sprinkler acts on that, but the drops are actually too large to interact with the flames themselves. They pass straight through. So what the drops do is they interact with the surfaces. They cool surfaces that haven't gone on fire, reducing risk of spread, and they cool the surface producing the pyrolysis gas, so that the pyrolysis rate is reduced, so there is less flammable gas to burn. Water mist, on the other hand, has much smaller droplets. They do interact with the fire at the flame level in the gas phase and interrupt gaseous flaming. They do also cool the surfaces, but not as well as a deluge system does. And the water mist, because it is involved in the gas reaction, doesn't actually reach the fuel behind the flame, and so if there's still a source of heat, pyrolysis will continue. I looked into published research on what water mists do to fire, and I found, largely speaking, 5 series of tests, or individual tests, discussed in the literature. Details of these are found on my website. Let's have a look at a few of them and just some specific observations on those tests. In general, though, general observations, it's been observed that water mist systems are beneficial, have a beneficial influence in temperature, but they generally reduce, indeed sometimes destroy, visibility in the locality of the fire. However, they occasionally result in an improved visibility at locations further away from the fire. The growth rate of the fire is generally observed to be slowed. Occasionally the fire growth rate is halted altogether. Sometimes the peak fire size is reduced. Fire spread is often, but not always, prevented, and the tunnel structure is generally protected. But as I said, they work by interrupting the gaseous flaming reaction. They do not cool the fuel itself, except indirectly, and that also means that production of carbon monoxide and other toxic gases may be increased. But here are some specific observations on specific tests. This is an observation based on a pool fire test carried out in a Vergolo tunnel in Italy in 2005. The graph here, as you see, that covers the span of 16 minutes of the pool fire. Burning is indicated, and for part of that time a water mist system was active. As you can see, before the water mist system was activated, the visibility in the tunnel was reduced in the locality of the fire, but as the water mist system was switched on, the visibility reduced to 0 in the locality of the fire. Conversely, the carbon monoxide production went up radically as the system was switched on, reaching a peak of 50 parts per million carbon monoxide. Interestingly enough, the temperature, there was an instant knockdown of temperature when the system was switched on, but eventually the temperature, even when the water mist system was active, did reach quite a high level in the tunnel, reaching a peak of 220 degrees somewhere reasonably close to the fire.